So, good evening. I request Professor Jairam Chenglu and Professor Pawel Moskal to come to the stage. So, good evening, dear friends, esteemed guests and colleagues, and dear students. It's with great pleasure that I welcome all of you to this public lecture at TIFR. This is organized as a part of this conference on frontiers of gamma ray spectroscopy 2025. This is a fifth edition of a conference which started in TIFR in 2009. We have been discussing about the recent advances in the gamma ray spectroscopy, mainly for basic research in nuclear structure and nuclear reactions. And we also have applications of gamma ray spectroscopy, which is discussed. In this public lecture, we have Professor Pawel Moskal from Jagiellonian University, Kraków, Poland. And he will be talking about recent advances in gamma ray spectroscopy from fundamentals to applications. So it will be a comprehensive talk on subject of science, technology, and its application in medicine. So, yeah. Now I request Professor Jairam Chenglu, Director TIFR, to give introductory remarks.
Yeah, thank you, Professor Palit. I'm delighted to welcome all of you for this talk. As probably many of you know, research at TIFR now covers a very large range of areas, but nuclear and high energy physics has been from the very beginning one of the core strengths of this institute. And in this area, as well as many others, TIFR also has a long tradition of not just doing excellent research, but also developing cutting-edge instrumentation with which enables this research. And as we just heard, all of these aspects are being discussed in the ongoing fifth edition of the Frontiers of Gamma Ray Spectroscopy workshop being hosted by colleagues from the Department of Nuclear and Atomic Physics, with participation from scientists across the country and beyond. And as we also just heard as part of this workshop, we are also delighted to present this public lecture by Professor Pawel Moskal. Having public lectures is also part of TIFR's long-standing commitment to public outreach. That is part of our effort to communicate the latest research being done here, as well as elsewhere to the public. So for those of you who are coming for a public lecture for the first time, please do check out our webpage and social media feeds for the details of upcoming events. Today, we are very fortunate to have with us Professor Pawel Moskal, a very distinguished speaker who's going to talk about gamma ray imaging, a topic with very wide applications. You'll shortly hear a more formal introduction of the speaker, but I would like to take this opportunity to thank him for accepting our invitation to come here to TIFR, as well as our invitation to give this public talk. So welcome again to what I'm sure will be a very informative and enjoyable talk.
Thank you, Professor Jairam. So now we request you to give a small present to today's speaker as a token of appreciation. So before we start the talk, so I'll formally introduce Professor Pawel Moskal. So he is the head of the cluster of nuclear physics department and the head of the particle physics and applications at the Jagiellonian University in Krakow, Poland. This is one of the oldest university which started in Europe in 1368. And he's also the co-founder of Center of Medical in Jagiellonian University, which is a flagship project. He is an inventor of cost-effective positron emission tomography setup. He conceived and headed a medical experiment demonstrating the first positronium images of human brain in vivo. He has been awarded many prizes, including Prime Minister Medal for Merit and for invention of from Minister of Education and Science Award and Minister of Science and Higher Education Award. So, Professor Moskal.
Good evening, ladies and gentlemen, dear friends. I am happy and pleased to have this chance to give this prestige public lecture at the conference, which is devoted to the radiation in nuclear physics. What the conference is about is a basic nuclear physics. And what I would like to present you today are some possible applications and maybe even future applications of that, what you and what we are doing in the basic science for medicine. So the nuclear physics has applications not only for the energy, the ecological energy production, but also in the medicine, and I will present you that. I am coming from Poland. I'm showing that map because I heard already, so here is India, at some places that Poland is an island somewhere north. So in some far countries. So it's still not an island. It's we are with the populations like about 35 times lower than India. So it's 35 times. So it's difficult to compete with you in any aspects here, but I will show you that anyhow we can do still something there far north. This is a few photos from the city I am coming from. It's very attractive touristic city, so you see a crowd like in Mumbai almost. So if you would come, you would feel good. And my travel here was funded by the rector of the university, and I learned that this is going to the YouTube, so I have to price my university, which is not a problem. So I am coming from the Jagiellonian University, which is probably the best university in the world. This was founded in 1364. So also one of the oldest in Europe. And that building here is a building which we still have in use, which was purchased, not built by the purchase by the king at those days for the university. Maybe that my claim is somehow confirmed by our best student so far. So this is our best student so far, Nicolaus Copernicus, and he studied astronomy. So he learned astronomy at our university. Now, this is a group which I will present you results and some concept from the group. We call ourselves, you have heard JPET, but this is an abbreviation from the Jagiellonian PET, and the Jagiellonian is the name of the university, and PET is coming from positron emission tomography. And this is one of this imaging with the radiation. And we are combining physics and medicine. So, and it's not easy. One has to have knowledge in both. One cannot be only being physicist. I learned one cannot really understand the things from medicine and vice versa. So we are guided a group by Professor Stempin, who is a professor of medicine, and I am a physicist. So this is our group. It's about 40 persons, about 20 PhD students and 20 researchers and technicians. And one of our best scientists is Dr. Sushil Sharma, who is also here with us. And we are very, very happy that he joined our university. He is an assistant professor, the first who got such a position from, not only from India, from at our faculty. And he will talk about the basic science we are doing during the conference, and I will concentrate on the medical aspects, just to show you that it's interesting, at least this is my aim, then it's interesting to make this basic science then for medicine. And I will start from some disclaimer. This is an image of the brain, and the upper panel is the magnetic resonance, the nuclear resonance imaging. So there is a nuclear resonance imaging. I will not talk today about this, but just to tell you, this is typically in hospital known as a resonance, this nuclear resonance imaging. And this is showing the distribution of hydrogen atoms in that case in a brain. Hydrogen atoms. So you see here a distribution of hydrogen atoms. Maybe if you could look closer, you could recognize this is an image of my brain. Maybe I stay like this. It's a proof that I have a brain, but maybe more interesting is the next panel, the next row, which is showing how the brain is functioning. So this is kind of, it's called morphological or anatomic image, or what tissues are, and this is showing how they are functioning. And I will today concentrate more on that part, which is under continuous development and exciting. This is also the image of my brain. I was injected some receptors of adenosine, and the researchers were looking how the brain is metabolizing or using that adenosine. So the colors are telling where is higher or lower metabolism or the receptor density of that adenosine. So this is telling about the functioning. And the disclaimer is that it was 23 years ago, so I don't know now. Just that. And today I will tell you, I have prepared also that basics which lead to the medical applications, but I will not talk about the matter-antimatter asymmetry or quantum entanglement. This will be covered by Dr. Sushil Sharma. I will present you how we are developing that, what we call Jagiellonian positron emission tomography, and invited by me positronium imaging. And since I am afraid that I could not come to the end, I will show you the result and then relax and explain step by step. So the very basic of that imaging and of what I am talking today is the gamma radiation, but also in general the radiation. And what is used in the positron emission tomography is the radioactive fluorine. So here I make an animation how the fluorine, which is from nucleons, is radiating positron. Positron is an anti-electron, so when it meets the electron, imagine this is in our body. We can take a radioactive fluorine. Imagine this is in our body, so that, I will show it once more, that annihilation of electron and positron is going in our body. They are disappearing, and we have the gamma radiation. And what is amazing, and this is what is quite new, but in physics it's not new, but for the medicine, what we are developing is new, that when I learned it some years ago, I was really amazed that in about 30 to 40% cases, before annihilation of that electron and positron, even if it is in our body, the positronium atom is formed, an atom from electron and positron. And this is happening inside our body. It is not used by now in the medicine, that information. So what I thought is, let's take, in nuclear physics, we have a lot of isotopes. For example, scandium. Scandium is decaying to calcium, but so this is a nucleus which is changing from, the proton is changing to neutron, and as it was before with fluorine, positron is emitted, but this calcium is excited. It has energy, and it's de-exciting via emission of the gamma radiation, the subject of that conference. And in nuclear physics, or in nuclear objects, that the excitation is typically, not always, but typically in the time of picoseconds. So if we measure the time when it was emitted, we know when the positron went to our body. And this is the basics for studying how long that process which you observe here took place, or how long that positronium was living in our body. And now I'm starting from the end. This is the photo. We came to the stage of the clinical studies with that method. And during the talk, I will explain all the details, but this is the photo from the final experiment. Here is a patient. This is a photo of the patient inside that tomography system which we constructed at the university. So you may imagine, it's not a company. In the university, you have professors and students. None are good for working in the lab, yes? So, and we manage that. So this is, in some sense, really a simple system because of the technology. You see here some detection modules. And I will not go the full medical procedure at this beginning, but maybe the interesting is that that patient was ill, has a glioma in the cancer. And with glioma cancer, the patients typically live, unfortunately, about 1 year. This patient was living already like 11 years and was still in a quite good condition, because of the nuclear physics and because the professor who was doing that studies with him, Professor Królicki from Warsaw University, was injecting to that patient through the catheter, let's say the hole in the scalp, the actinium. Actinium is isotope which is emitting alpha particles. And that actinium isotope was attached to the substance, to the molecule called substance P. And substance P is not that I don't know what is the name of this molecule. It is just the name of the molecule, substance P. And this is such a molecule which have a high affinity, which means it's with high probability attaching to the receptors, to another molecules at the surface of the cells of this glioma cancer cells. So here you see a pictorial example of some cancer cell with the receptors, and these molecules, when it's coming close to such a receptor, is just chemically interacting and attaching to this. And if it has actinium, that actinium is emitting alpha particles and it's killing the cancer. And there are not so many of such receptors in the healthy brain, so like 100 times less. Therefore, one can kill a cancer, but not at the same time save a brain. And this is why we did an experiment together, in order to control where these molecules are going in the brain. These professors, these medical professors, were adding also the gallium. And gallium is emitting positrons. So they were adding gallium just to make also a tomography to see where it is. So you see the gallium is emitting positron. Now it's similar to what I told before, but with part of the molecule in the brain. This positron is then going through the molecules in the brain and may annihilate with the electron. And these are these two radiation gamma rays, which are also here shown. And we register that rays. And from that, we make an image where this gallium is, which means where this substance P is. And this substance is attaching to the glioma mostly, so we know where it is. But they may also form these positronium atoms. So we can also measure how long they are living that, because this gallium is also, after emission of positron, becoming another nucleus, thin, but this is excited. So it's again emitting that additional, the excitation photon, or gamma ray, which is shown here. So we measure the time when this was emitted, so we know the time, which is the same time within a few picoseconds when the positron went to the brain. And we know then from that blue rays, in quotation sign, of course, they are invisible. From that rays, we know where it was and at which time. And this is the main result, which is very new. This is an image where this substance concentrated in the brain. And it was mostly concentrated in that glioma. And in the healthy brain, there is almost nothing visible. One see here something in the salivary glands, but this is from the other part of the treatment, which I was not talking about. So this is not from that. This is because of another substance which was injected before. But this is what is from that gallium. So we know that the actinium were here and the actinium was killing that brain. It was only a little events when this additional gamma was there, because I will now change back, because that tin is emitting that gamma only once per 100 times, only in 1% cases. So the statistic was low, but anyhow, we are able to measure how long these positronium atoms are living in the glioma cancer and in the healthy brain. And color here is telling a time. This time is in the order of nanoseconds, so like about less than 2 nanoseconds, 10 to minus 9 of a second in a glioma cancer, and quite longer in a healthy cancer. And it was for us like showing that the method works. One can make a map of positronium atom properties in a living human being, but what we could not predict, and this is like it is, and it's very promising, that the times are different depending on the healthy or cancer tissues, which means in principle one can develop it further, or there is a reason to develop it further for distinguishing between the cancer and healthy tissues, so giving additional parameter for the doctors for the diagnosis. And I will show you later that this can also be good for the oxygen concentration diagnosis and this kind of things. So this could have been an end of the lecture for professors here of the nuclear physics. But since this is a public lecture, I would like to explain now everything such that I hope also I was told that the pupils from the school will hear it, that everybody can understand what was really done and what is coming from nuclear physics to obtain such an images, and also some other things. So I have mentioned alpha radiation, which was the actinium. Beta radiation was that positron from the fluorine or from the gallium, and it was gamma radiation, which was from the nucleus. So there are 3 types of the radiations, and I will now make a nuclear physics lecture. It will be 5 minutes, which I am sure afterwards everybody will be good in nuclear physics. So the alpha radiation can come from the large nuclei. So inside the nucleus, everything is, these nucleons are moving. And exactly the same as in the large group of people, if there is a large amount of nucleons, large amount of nuclei, then they try to make intrigues, clusters, and some are separated. And these clusters, which are going out with typically 4 nucleons, like helium nuclei, are called alpha radiation. And this is radiation which is having charge equal to 2 because of 2 protons and so on. So this is one kind of the radiation. Then the other one, which is good to know also for medicine, is that beta, which was emission of that positron. And now this is not so easy to explain. In fact, this is maybe we can come even to the philosophical discussion. In that case, proton, in that case is changing to neutron, so one kind of matter is changing to another kind of matter. We are getting even another type of the matter. So one can go now in the particle physics, explain that it's not neutron changing to proton, but there is one quark changing to another quark, but it's not a change. It's also only one step deeper. So this is very mystic, I would say, reaction. And then the gamma comes from the fact that nucleus can be excited, as you see here, having a lot of energy, and it can de-excite by emission of the gamma radiation, electromagnetic wave. It can be even, then it becomes less energetic, emitting another one, it can become even less energetic. So this was origin of the radiation from the nuclei. But as you also seen that the gamma radiation can be also from the matter-antimatter annihilation, as on that example here. So if for example, electron meets a proton, this is a matter, and antimatter, they may disappear and only the electromagnetic waves are coming, which are the gamma rays. So this is all about the origin. So half of the lecture is done. So this is for the professor. This will not take too long. Now, how to detect that? Because we have to somehow detect that radiation to make an images or to make some, to gain some knowledge from that. And this is my imagination of the matter. There are atoms. Everything is simplified. And then if such an electromagnetic wave comes, this radiation, it may kick an electron. Electron has a charge, electromagnetic wave, electric field. It may kick out the electron. This was called, for the explanation of the effect which you've seen here, I will show it once more. When this gamma is disappearing and the electron is going, Einstein got the Nobel Prize. So this is a electromagnetic effect. Also, there is another Nobel Prize in that nuclear physics, which Compton got for explaining how it goes when the gamma is not disappearing. And we are using these 2 effects mostly in our studies. And now, as you've seen, this electron is ionizing the atoms. or molecules, so there is a charge. So by measuring the charge, we have a current signals, and these signals are giving us information about this gamma. But it may also happen that excited atoms or ionized will emit photons, because the electrons from higher orbits will go to the lower, and we will have a lot of photons, and then we register that photons. So this is then a typical detector, which will register a gamma radiation, makes the photons inside, then these photons are converted to the electric field, electric signals. And I will show you, I am close to finalize this description. I will show you how we started with the tomography, which I am showing you today, and how how pleasurable it is to see these signals. So here you see, like from the laboratory, a simple example of the detector measuring the gamma radiation. A source was here emitting radiation, these positrons, then one gamma was going here, the other was going here. Here is that material called scintillator and converters, photomultipliers, which are changing light to the electric signals. And this is the lab. You see our first prototype of this tomography system. So this is the first prototype. Here you see we started to build the second prototype. It was quite long ago. And this is, I am showing that because this will illustrate you how it works for the professionals, and for those who see first-time signals, you will see signals in the nuclear physics. So I put different colors to that converters converting light into the current. And then if the radiation is in the center, then gamma are interacting here, photons are flying here, the time to come to blue and to green is the same. So the signal starts at the same time. They should be the same, but this is never the case, they are almost the same. But start at the same time. And this, because the distance here and here is the same. Red and yellow also starts at the same time. And they are more or less the same. So this is in real life we have never ideal situation. And you may see like in front of the aquarium and enjoy the signals in the lab. So this is pleasurable. And if this is at the center, they are starting at the same point. But now you shift that collimator and you see a shift. The blue is coming later, and this is visible. So you shift it by some centimeters. This is light, but the devices are so sensitive that can measure even hundreds or even tens of picosecond differences. So we see the blue is later because it's longer distance, the green is earlier, and also the red is later and the yellow is earlier. But one can revert that, like telling, okay, now I look at the scope, at this oscilloscope, I know that time interval, so I can reconstruct where it was. And this is the main principle of how these position-sensitive detectors, which are large, may work. And these are a few more signals. And one more thing here, interesting. This is from photos from real lab. The blue is farer, so less photons will reach here than to the green one. So therefore, these blue signals are lower than the green one. This is another information we can get to reconstruct the position, and we also can reconstruct the time. So now I will go to more detailed discussion about what we are doing. I think now everybody is knowledgeable what the nuclear physics is about, where the radiation comes from, and how we can measure this. And the main aim, and I show you also some result of that group which I have shown you, and mine at some point, was to make the tomography low cost. I was hesitating for a moment because always the first word which is coming to my mind is to tell cheap. But I am always teach, do not tell cheap, because it does not sound good. So maybe economic or whatever, but this just making the tomography cheap, and I will tell you why it can be important. And that with that positronium imaging, I have shown you some images to make it more specific, which means that we get more information that now about the ill tissues. Because it's not so easy to determine whether what you see in the tomography is a cancer or not. It can be inflamed cell, it can be infection. It must not necessarily be a cancer. And the reason to make this tomography cheaper, the tomography which is enabling to look for the functioning of the tissues at the very early stage. It must not be a growing tumor that you see a change in the tissue. It's just a change at the molecular level, which one can see with that. And if you look at that map, which is quite recent, you may see that there is more than 60 countries in the world that has even none of the tomography system. Most of the countries has something between 0 and 1. And in Europe, few countries has more than few per million citizens. So as a physicist, we often tell like in the first order. So I think the true sentence could be when looking at the map is that nobody in the world has access to that tomography in the first order. In India, you have almost 300 of such devices, which sounds a lot if one would not know that India has more than 1 million citizens. In Poland, we have about 30, but it's still less than 1 per citizen. Here you have about 0.3. So it's not available for most of the people, and this was the reason to try to find a more cost-effective way. And this is how the project or this research is going. So it is not like one-day research. This is also maybe a lesson for those of you who are just starting. One cannot develop technology within a year or two. It's a new technology. One has to be patient. So this is a first prototype, which I have explained you how it works. But it's impossible system of that because one would need thousands of oscilloscopes. So it would not work. This you have seen standing there aside. And then each of the prototypes, new generation took few years to build. I was more optimistic here in my first presentations when this was not existing and this was not even a concept. I put here 18 or even 17. Then I changed to 18. Then I had to change to 20. So it took about 4 years later than expected. Therefore now, for that last stage, which is a total body, I put already 2028, and I have a slide ready for 4 years. And maybe within that time, I will show you we will really manage to come to that system. So to acknowledge what these changes which we are proposing are, why it is more cost-effective, and what are the advantages, I will start from explaining you, because I assume not everybody here, and I was told is a nuclear physicist, how this works in a little more detail, the tomography. So you already seen the fluorine. I don't know if one can see it, but this is F from fluorine atom, which is attached to the glucose molecule. And this is that glucose is the most used molecule for the tomography imaging. It's in more than 90% of cases. This is attached to that molecule, and this fluorine is radioactive. So the patient is injected glucose. Glucose is metabolized, distributed over the body, and then we are measuring with the detector those gamma rays. and from the gamma rays, there are many of them, one can reconstruct that places where, we reconstruct the places when the electron and positron annihilate. These are places where the fluorine is. This is a place when the tissue uptaken that molecule. So we are at the end getting a distribution of how fast this glucose is metabolized. And cancer cells are metabolizing with a different mechanism that glucose that healthy cells, and they are using about 10 to 20 times more. So if there are cancer cells, we will have much more of this annihilations. So here you see a little for the biology, what we can learn from that. So assume there is this glucose in the blood or in the plasma, then the cell can uptake that glucose via some transporters in a surface. And then once this fluorodeoxyglucose is here, it will not be normally metabolized because there is fluor. So it will stay there in the cell until the fluor will change to the oxygen, as I have shown you before. Therefore, measuring the places of annihilations, we are measuring the rate of that uptake. But also another information which doctor can get is what is the density of some specific receptors at the cell. So if you choose, as I told you before, for example, this substance P, which is specific and attaching to some kind of the receptors, then healthy cells may have like 100 times less of the receptors than the ill cells or cancer cells. So by injecting such a substance which is attaching like this one symbolically with the radioactive nuclei, radioactive atom, it will attach to that. So there will be a lot of radioactive atoms around the cancer cells, but only a little about the healthy cells. So these molecules are not wise. They are not a human being. They are not searching, but they are just everywhere. And if we choose them in a clever way, they will at some point concentrate around those cells which has a lot of these receptors. So one can measure with that method either how fast glucose is metabolized or what is the expression, it is called expression of receptors at the surfaces of a cell. And now I will show you in the simplified way how one make an image. This was maybe also clear from that figure before, but let's say, and this is a simplification, that all that glucose with the radioactive fluorine was concentrated in one place in the brain. As this is not real, but just example to explain. So then from that place, we will observe these two gamma rays. And they are going always back to back because of physicists know because of the momentum conservation. And this is kind of the natural that it will go back to back if at the first stage it was not any movement and then one go one direction, the other must go the other directions. And we measure them with that converters, which it's too much simplification, but it can be seen like something inverse to the bulb. You put the light here and you are getting a current from the other side. It's very large simplification, but it may be seen like that. And then we measure a lot of them. Typically, few example you see, it would be very easy to just from seeing the cross point of the lines. But of course, if there is even two, then it's more difficult because if we look for the crossing of the lines, we will have also a crossing at the other positions. But then we can count how many times the crossing occurs in which position. So, and give a color to the number of this crossing. So crossing 1, I gave a color, blue color. Here it crossed 3 times. I put the red color, and you are getting an image with a background. These crossings here will be the background, and then more number of crossing will be the places where really some annihilations are taking places. And this is not that much simplification how it really works. The next is to find out the mathematical ways of making that more effective, and this is then not anymore this physics phenomena. One more thing is, for those who are maybe more expert, is if one measures a time, in addition to position also a time, then from the time difference, as you've seen at the scintillator also, we can guess how far from the center this annihilation was. So if the time here and here is the same, then we know it was at the center. If the time here is earlier than the time here, we know it was closer to here. But this is done with some precision. Some of the tomography system nowadays has already such a system for time with the 600 picosecond precision, and then it's like already shortening that whole line to about 8 centimeters. But this is already very helpful, because out of such an image, you can shorten those lines, and you have less of these crossings, which means one can get a cleaner image with the same amount of the radiation going out from the patient. So this is why you would have a better timing. Nowadays, some not so many, but the best one has even 200 picoseconds, so then it's even better. So now I will make a short break to tell you an anecdote, because I am from Poland, and here is also one other professor from Poland, so I will prize Warsaw, and will tell you a story. The first who discovered radioactive fluorine were the Polish scientists in Warsaw. Professor Wertenstein asked his student to put an alpha emitters and irradiated nitrogen, and they saw what is remaining. Chemically, they recognize this fluorine is still radiating. And they wrote a paper, artificial radio element from nitrogen. It was Nature. Everybody knows how difficult it is to publish in Nature. 1934, 133, and the page is 564. I am telling that by purpose, because if you compare that, so this is everybody knows, Irene and Frédéric Joliot has studied a different reaction, alpha particles of boron, noticed that the nitrogen is radioactive, and has published a paper. Nature, the same year, the same volume, page is different. The title here is Artificial Radio Element, Artificial Production Radio Element. And these two got the Nobel Prize. And about these two gentlemen, only Professor Pawel Napiórkowski knows in that audience. I am pretty sure. I am pretty sure. The difference is the page number. Maybe there are also some. Maybe there are also some other differences, but I will let you to conclude yourself from that story. So let's then continue. Detectors, the tomography system, are using crystals as a material when this radiation is registered. And that all of them. The crystals are very expensive. They are the most frequently used are called LiSo, lutetium, yttrium, silicon, and oxygen. So these are elements, and this from which these crystals are grown, and they are like in the price of about 1/5 of the price of the gold. So the tomography system are therefore very expensive. So the recent one, which I know, which was purchased in Warsaw at the Warsaw Medical University, it's about 3 million euro for a detector which is 25 centimeters or so. 3 million euro to have such a detector system. So that's a huge amount. So what I proposed to change at some point, which was criticized a lot, that instead of that crystal, let's take the plastic scintillators. Plastics can be used as light guides. They are like about 80 times cheaper, 50 to 80 times cheaper in the production than the crystals. So then one can get rid of, and important is that material of crystals constitute half of the price of the tomography system. The other half, more or less, is electronics. So with that solution, one can decrease the price by a factor of 2 immediately. But there is also another advantage, that it can be large, because one can put that photomultipliers at the edges, make it large. And as you've seen already at that photos I was showing you from the scope, even if the scintillator is long, we still have a lot of light at the ends, which is not the case for the crystal. So these are it was not easy to make it, because the experts were criticizing that there is no photoelectric effect, which is true, because plastic scintillators are from the carbon and hydrogen. Both are too light to have significant fraction of photoelectric effect. But I can, so the progress was delayed by many years. Then I tried to change in the grand application plastics to polymers, but the experts are not ignorant. They recognize that polymers are also plastics. So the grants were rejected. It took many years, but now, so one reason was the no photoelectric effect, and the other was that the efficiency is low. And it's indeed lower, because the density of that plastic is about 7 times lower than the density of the crystals, which means 7 times less electrons per cubic centimeter, roughly. But with that construction, we can make more layers, and we can make it larger. And these two facts are compensating for the lower efficiency. And why the price is lower are these two factors. One is that the scintillators are about 50 to 80 times cheaper. And another is that the electronics or photomultipliers, these various converters, electronics boards are proportional here to the cross-section of the detector. And in those solutions which are in the hospital, which you see here, the surface is covered with the detectors. So one reason is the much less price of the scintillator, and another is few times less electronic elements. And at the end, one can make it 5 to 10 times cheaper, depending on what is the length chosen for that detector. And here is now a real disclaimer. You think is it simple? It took us, it's about 40 patents of different solutions to make it works, this system. And now I will show you some results from the first prototype, which was in the laboratory. So here you see those scintillators. They are covered with the black foil just for the light tightness, photomultipliers. This is to see how it is in scale. We had 3 layers. Therefore, on some slides, you have seen 3 layers. And now this detection system was also made in a way that we can measure annihilations into 2 photons, 3 photons. If there is the excitation photon, there is no a standard coincidence system. It's just in that new generation way of registering, which is called triggerless, which means we register just everything. And then the analysis is offline to get to select the signals. So this is our first prototype, first phantom. Phantom is something pretending an object. In that case, we are pretending a human being by a cylinder. The sodium source was in the stomach. Here was on the skin, and annihilations were at the edges. And we were so happy to see that we can reconstruct that surface, which means make an image of where the annihilation takes place. This is with using more iterative procedure. But with that detector, we could also make free photon images, like when positronium annihilated into free photons. So this is the first ever free photon image with the tomography. So that system allowed us to make many new things. And then for the positronium, we took that sodium. Sodium, after emission of positron, is also emitting that additional photon, like scandium. And now, maybe for the expert, one can ask yourself a question. You have no photoelectric effect. So how you distinguish the annihilation photons from the excitation photon? Typically, the excitation photons in the nuclear, the excitations have one million electronvolts, and this from annihilation has 500,000 electronvolt. But this is a spectrum, and this is a here you see articles of Dr. Sushil Sharma explaining that in detail. This is a Compton spectrum from higher energy gamma, and this is a Compton spectrum from the lower energy gamma, and this is from some scatterings and free photon annihilations. So just taking signals larger than some threshold, we know it was the excitation photon. And then we can identify that photon. And this is a spectrum of the time difference between the emission of the excitation photon and these annihilation photons. So you see the accidental coincidences. Now I will explain later the short-lived parapositronium and long-lived orthopositronium in that material, 90 nanoseconds. So this is the logarithmic scale, again for the experts. So this is telling that there is long-living objects in that material. Now, another question which one asks oneself is how at all this positronium atom can be created in a body or created in a material. And this is a simplified explanation, but in general, I think illustrating how it really works. So let's think about the scandium emitting positron. Then this positron is ionizing the molecules or atoms, which means kicking out electrons. And then the lower energy, the more frequent are these ionizations. And at the end, there is a lot of free electrons and that positron. So that positron may form with the free electron and positronium atom. But to live for some time, it must find a free space. Otherwise, the electrons from the atoms would kill it. So this is a hemoglobin, part of the hemoglobin molecule, as much as one can to scale. So these molecules in our body are from thousands of atoms. And there are free spaces in between these atoms. So such a positronium atom, when produced close to such a free space, may live there until it decays. And there are two possibilities to form such an atom. One is when, for the physicists, when it has spin 0, or when it has spin 1. Also for the physicists, one is turning and the other one is not turning. The one which is turning lives longer because it's more difficult to annihilate. The one which is not turning, having spin 0, this is a simplified explanation. One can explain it in a different way with the symmetry violations, but I think it's quite okay. And this longer living lives on the average 140 nanosecond, and the shorter living lives 120 picosecond. It's more than 1,000 time difference. So this one is then maybe useful for the diagnosis, because if you go to now it's again a hemoglobin molecule, as much everything as possible with such a simple tools to scale, which for the experts, you may look hydrogen atom and that positronium atom. The only difference when calculating the properties of these atoms is the charge is +1, -1, is the reduced mass in the equation. And the reduced mass differs by 2. So the size of the atom is 2 times larger than hydrogen. The energy levels are 2 times more denser, everything by a factor of 2 or 1/2. So this is 2 times larger than hydrogen and more or less to scale. So even in our body, the spaces are large enough that it can decay to the free photons. I've forgotten to tell. And this comes from the symmetry conservations. I can explain later if somebody likes. That this long living is decaying into 3 gamma, and this short living is decaying into 2. So it may decay to 2, 3, but if the positron from that long-lived atom is interacting with the electron from the surrounding atoms, it will mostly annihilate to 2. It may also happen, and there is a lot of oxygen molecules in our body. These are the molecules for metabolism. That oxygen molecules are also turning. They are paramagnetic for specialists. So if 2 turning molecules are meeting, they can exchange the spin. So the one which was turning may become not turning and then is annihilating 1,000 times faster. But this is then going to be exciting because the lifetime of that atom will be shortened, and will be shortened by the oxygen molecules which are inside our body, and it also will be shortened by the interactions with the surrounding atoms. But here one can tell the larger are or the smaller are those voids, the more probable will be that interaction. So by measuring the lifetime, we are getting access to the size of free voids of the porosity of that molecule, so intramolecular structure, and we are getting in principle information about the concentration of oxygen. And it is a known effect that for example, the more aggressive the cancer is, the less oxygen is in that tissues. So, there are no good methods for the oxygen, in vivo oxygen determination. Here for the biologists, I have put here an example. This is the partial pressure of oxygen. So pressure of oxygen in the various tissues. The number of the tissue here is given the name, like a brain, kidney, different names of the tissues. And the cancer tissues have always, on the average, lower oxygen pressure, so less concentration than the healthy tissues. And that difference can be converted to the lifetime of positronium atom. So our first studies were, we could not go with that detector to the hospital. 10 minutes, thank you very much. So we could not go, you can imagine, it took us half a year to set up it in the laboratory. So we did first the measurements, just taking tissue operated from the patients. And for physicists, it's easy, so that we need this knowledge from Professor Stempien and the medical colleagues. So it's easy to tell, but then think what, how, and which tissues. So here we put the cardiac myxoma, the tumors from the heart, and here was adipose tissues inside, operated from the patients with the sodium inside. And then you see here the standard image showing where these tissues are. But for each voxel here, we can register also that additional the excitation photon. And for each, in the three-dimensional image, pixel is called voxel. For each voxel here, you can make a lifetime spectrum. And from the lifetime, we can extract how long positronium atoms are living. And this is the result. And exciting here was, so this was the first image, but not of the human, but made in the lab, so-called ex vivo, out of the organism. And we noticed that the lifetime of these orthopositronium atoms in these tumors was, here in the green region, was lower than much lower than those adipose tissues, the fat tissues. And this was done for many patients, and the difference was always significant. But to go to the hospital, we have to think further. And this is now one of the main parts. So we then constructed a tomography system, which you see here, from plastic scintillators and silicon photomultipliers. One module is 2 kilograms. So the full tomography system is 50 kilograms compared to tons, 1-2 tons in the hospital. This is a photo of the detector with the superimposed patient, not a real patient. And this is what the detector can measure, which photons. First, the student makes a photo session in the lab. We prepared like two hemi-cylinders. Just we wanted to be prepared before going to the hospital. Then this is an installation. The tomography system we just transported in by car from Kraków to Warsaw. This is a professor who was one of the only so open-minded at those days that went into that collaboration and allowed us to do that. This is the answer which I am always getting in Kraków. Why not in Kraków? Why you went into Warsaw? This is like the answer why, like somebody from Mumbai went to Delhi doing experiments. I think more or less. But this is an installation of the tomography system. So we are just rolling inside. Then after tens of minutes, it's on a patient bed. Here you see two other excellent Indian PhD students in a group. And this is the first movie, how we did the measurements. The ethical committee gave us 10 minutes. So we had 10 minutes to come with the tomography system, to take the data, image, and to go out. And this we could manage only because of that features which that tomography system has. So this was like a movie, but in fact, nobody even made a movie. Nowadays, everybody's making a movie, but these are only few photos which I did, looking when it was put there. There's maybe 5 photos. And this is the result. So we are excited to see that there are organs like spleen, liver. This is a cross sections. Then, so it works. Even in that prototype phase with the plastics, it works. And then some experts from various companies are telling, but this is low resolution. And therefore, I learned not to tell immediately, but after some time, that this is our, and this is Siemens, which was behind. So, and this is not optimized. We are just having not optimized conditions, and we have no software for all the corrections by now. These are photos from another hospital, then in Kraków, from another patients. This is now here a comparison to General Electric tomography system. But now what I wanted to tell, which is hidden by that talking FIG-25, here is titanium scandium. Titanium is decaying to scandium, and the lifetime is 60 years. So now, if we would make a titanium scandium generator, so taking titanium, putting it to the glass, and having a proper acids or some to elute scandium, there exist such generators. One could, in principle, have such a generator with scandium for many years. And this is now the suggestion. It's a little exaggerated, but it, I think, opens the imagination. One can put this 50-kilogram tomography system with closing, opening, take a scandium germanium generator, or now there is germanium gallium is now living 1 year, so even 1 year, and one can go with such a car and make a tomography wherever. And this is what I would like to advocate. I know that you maybe also here could be interested, or I give you a reason why it would be good to produce, for example, titanium-44, or to elaborate a method for making titanium-44 here. And then all the world will become accessible with such a system. So this is what I wanted to advocate you. Now coming to this positronium, I already explained that things, and we were thinking to make this experiment with scandium. And there is like close to that Warsaw University Hospital, there is a heavy ion laboratory, when it was a special project for many years when they are able to produce scandium. But by now we did not got the ethical committee consent for doing that with scandium, so we have to still work on this. But we used the scandium for calibrations of the detector. So we made measurements with gallium. And gallium has also that additional gamma, but only in 1% cases. And therefore, it was so low statistic. And this is a photo from when this patient was studied, which I explained you before. So we just, again, this was a Siemens tomography. I forgotten to tell you. And you used the Siemens bed, and the patient was shifted through the tomography to our system. And the head was here. And this I already explained. This I have you explained, but now you see how it really works. And I put also here this actinium is emitting 1, 2 in a cascade of decays 4 alpha. Therefore, it's such a good killer for the, it's like depositing in the cell 4 alpha particles. I am close to the end. This you already also seen. We are now doing another experiments now with different body parts and building that detector for the total body. And we already got the money from the ministry to build that detector. And I will tell you, it sounds huge. We got from the ministry 3 million euro or dollars. And this is for building a tomography system for 2.5 meters. 2.5 meters, just that we have no border effects. And $3 million sounds large, but Siemens is selling a tomography system from 1 meter, 6 for, nobody knows, but almost everybody knows, from 9 millions. So now you can imagine, this is that factor 10, if you recalculate. But of course, there are other costs with the company, but this shows how much cost-effective this technology is. And I wanted to show you that with that detection system, we will be able to make movies, not only the like photo of where the pharmaceutical is, but also a movie. And there are already such systems in University of California, Davis. It was a 2 meter. The project was for $16 million, and the United company built such a system. And here you see the first such a movie. The patient was injected fluorodeoxyglucose, and then you see what is going on in the body. You see how that substance is distributing in time. So you can have additional information. I mean, it's nice for eyes, but so one can see various pathologies and anomalies even immediately by eye. But one can also see how the uptake of the substance is changing in time in a given organ. And this is differently changing for cancer and differently for the healthy tissue and so on. So this is what we will also be able to do with that. But in addition, that tomography system will allow us to make that positronium images. Having that, this will be 30 times more effective than the system we use in the hospital. Now, changing from gallium to scandium will be a factor of 100. So that images we will be able to make 3,000 times more statistical significant than you have now. And this scandium was also done by Professor Wertenstein in Warsaw. This is another interesting story. And this is the full paper, another Nature, the same year. No, this is different different volume, next volume. This is the full paper, Now we have to write this for 20 pages. And you know who reads, referees and those who are, and 2 PhD students who likes to learn from that. But this was half a page, and it was enough. And everything is correct here, except that they have no neutrino, because it was no neutrino those days and in that time. So it's very nice. And this we are now building the total body PET, and it will have an advantage because it's light. And it will be like a sunbed. The patient will be lying. We will make a CT image for anatomy, and then that tomography system, and we already built such a construction. This is a work of one of our PhD students from Turkey. There will be like the sunbed. The patient will be able to close and open this. And this will be much lighter than it looks at that figure. So this will be, again, an innovation for that system. And I have something for peace, but I will finish now because I see that I already exceeded the time. So thank you very much.
The excellent talk. And now we can take a couple of questions.
So thank you very much for this excellent talk. I have a curiosity. Why you need to make several layers, since plastic in principle one can do any thickness. So why do you need several layers? And the second question is why, since there is a lot of effort to make gallium, I think, what is which is, you say, 100 times less? I mean, the emission of than scandium. Why is this?
Okay, thank you for these questions. Maybe I will start from the last. We use gallium because gallium is now routinely used in the hospitals. And it is used not because of having this additional gamma, but this is used as an isotope which is easily attachable, for example, to the molecules like called PSMA, prostate-specific membrane antigen. So they attach this gallium to this PSMA and are looking whether the patient has, as an example, prostate cancer or not. So now this gallium is routinely used in the hospital, so we did not need any additional consent from the committee. This was the reason that we can use it, but this is not most effective for that positronium. And the question about the thickness of the scintillators, well, the reason is that in order to make a image reconstruction with the good spatial resolution, when good means below 5 millimeters or 5 millimeter, one need to know the X, Y, and Z of the interaction. And if the scintillator will be thick, then unless one finds a way how, but in the example which I was showing, we don't know in which place radially the interaction was. And these photons are spread such that at the end the information is lost. So having a thick scintillator would cause a deviation of that images, because so radially, for those photons which are going radially, it doesn't matter. But if you have that on the edges of the body, then there is misidentification of the position, and this is that size is defining how much it is incorrect. So then one would not get in images with precision required for that images.
Yeah, yes.
Yeah, very inspiring talk. I just want to continue from the previous question. So, number one, do we require to have more than one layer of scintillators to just avoid the cracks that you may have longitudinally? Second, do you want to comment a little bit about the other options for detector elements besides scintillators?
So these plastic scintillators are deteriorating, but all the scintillators are deteriorating. But the irradiation so one of the reasons could be radiation, but the radiation from that tomography imaging is kind of negligible, so this is not a problem. But they are maybe 1-2% per year decreasing on the efficiency of the photon transportation. But this detector system, this first one, we completed in 2015, and we do not see any degradation of the performance. But one has to do it in a proper condition. So one has to construct these detectors in the cleaning rooms without the dust, without any. So this must be done according to the state-of-the-art knowledge, not to touch with the finger, not because otherwise after some years it's really degrading. But we have it as an example for 10 years, and the performance was not changing. And this is similar with the crystal detectors. And now the other options, which are now is the crystal detector. So not plastic, but crystal. And this is not another, this is now the only option which is used in the hospitals. The difference between is the kind of the crystal. So the most up-to-date tomography system had this, what I mentioned at the beginning, LYSO crystal, LYSO. And there are still some which have BGO crystals, but with BGO there is no, they have like 300 nanosecond decay times, and there is no good information about the timing. So the time of flight is. There are now people are working on to extract also the timing information, for example, from the Cherenkov radiation, or in many are trying to find the possibility, but in the regular way, these BGO are too slow to give timing information. These lights are much better. The decay time is 40 nanoseconds, so they are much faster. So another option are crystals, and they are always used in the hospitals.
Okay.
Yes, thanks also for a very nice talk. So I have two questions. One is the time of flight that you mentioned in the beginning there. Are you implementing that in your system? Time of flight to improve the imaging? The resolution?
So we are. I kept that slide. So we are sampling the signals in a very cost-effective way. It was one of the solutions. I will hopefully come to that slide soon. So we have such a solution that the signals from the photomultiplier, here is the signal from the photomultiplier, they are typically about a few nanoseconds, let's say 5 nanoseconds. So they are very, from the scintillators, the rise time is about 1 nanosecond, the decay time is 2 nanoseconds. So the full signal is about 5 nanoseconds. But we anyhow sampled them, and we sampled them here on a voltage domain, just splitting that signal and putting directly to FPGA, to this field programmable gate arrays, and then setting a different thresholds there. So we are getting times, but there is no any analog in between. These are just fed directly to the FPGA. We are getting timestamps at the beginning, at the leading edge, and at the falling edge in that detector at 4 solutions. So at 4 levels. So from this leading edge timestamps, we are reconstructing the time of that signal arrival, and from the width, from the differences between, we just can make like roughly estimation of the area, which is the charge of that signal, by measuring the timestamp at the beginning and end of the signal.
But you have 200 picoseconds, I think, time resolution. So with that, you could do time of flight imaging.
So we have.
Yeah.
So then so what I was explaining is that for each interaction, we have a X, Y, Z, and the time of arrival of the signal, and the width of the signal.
So you have constant fraction in your FPGA somehow to get a good timing.
This is one could think about making like a in offline the constant fraction, but this is like a leading edge, this is rather not a constant.
Yeah, the other questions concern scandium, and I mean that's interesting, of course, from the point of view of the long half-life. You can reach over the world, as you said. The drawback is, of course, if this half-life would remain in the body, so the biological half-life should be much shorter, right?
But just to maybe I did not make it so clear. The titanium, this 60 years, is decaying to scandium with the half-life of 60 years. But then scandium, which is then, so we have to take care that only scandium.
Scandium, the daughter is way more, okay, so
4 hours.
In the generator you have
4 hours.
Okay.
So it's not, then even better than this fluorine, because can be easier transported if one would need to transport it, like making.
Okay, sorry, my mistake.
This is 4 hours.
Just wanted to revisit the time of flight question. If you understand correctly, LISO has a better time resolution than a plastic scintillator, like probably.
So in principle, one can get better timing with plastics than with LISO, because the best, at least now, the best tomography system with LISO are having time resolution of about 230 picoseconds, and this is full width half maximum of the time difference. Because we in physics use typically sigma of one interaction, and this 230 picoseconds is already full width half maximum of the time difference. So the sigma is much lower, and in our detector now with that system, we got 450 picoseconds, but it doesn't mean that we cannot have it better. In principle, one can have even better timing with plastics than with the crystals, because the photons are, one can say it, more dense in time. So what defines the time resolution is what is the probability density of the timestamp of emission of the photon in a given time interval, and we have all photons within 5 nanoseconds, and then in the LISO all photons are in about maybe 40, 50, more nanoseconds. But LISO have higher efficiency, so they are like in plastics typically there is like 10,000 photons per mega electron volt deposition, and LISO can have even like 50,000. So it's
is this a special kind of plastic scintillator that you developed?
No, this is we started from choosing the scintillators which are with the best possible or the smallest possible rise time, but then we learned that those scintillators have then lower path length of photons, or the higher attenuation of photons, because they are more in the blue or violet region. So finally, in the optimum, we are just using the most standard, which were in the former times called BC 408, which is 4 meters. Okay, this is again, in principle, they should have 4 meter attenuation length of the photons, but typically we measure always four times worse than given by the producer, because they give in the bulk and we measure in the strips.
Yeah.
So, yeah, when you introduced the FDG in your talk, you mentioned about the dose rate is something like 7 millisieverts in PET density correlation, and in the second one, it's like something similar to the average background radiation. So, is it something related to JPET?
Okay, this so you noticed that. So thank you. I was even not talking about this. So in a PET CT, the most of the dose comes from the CT. In the whole body PET, is in the order of 10 millisieverts, but the dose which patient is acquiring from the injected pharmaceutical is in the order of 2 to 3 millisieverts. And I use this comparison that this is just like comparable with the natural radiation in the most of the world, excluding part of the India when you have 50 or 70 millisieverts per year. In United Kerala, for example. Okay, I think this was not a joke. In Kerala, the radiation is much higher than on the average.
Okay. Yeah. I'm sure there may be more questions which we can continue.
But what was then the question?
So in PET CT correlations, okay, it's giving some more radiation dose, but in your case, without using CT, is it able to get the same resolution or same clarity?
Without, then I will tell you another anecdote. When some 10 years ago, when showing that concept, I was always asked, and where is the CT? And then you've seen that animation where the CT is moving over the patient, and because finally we decided to make also CT, and CT is used for the attenuation corrections. But nowadays, the computing power is improving so much that there is more and more articles, and now even implementation, then one can make these corrections without the CT. So I think after a few years, I will be asked, what for are you using the CT if one can make it just from the signals acquired with PET. So CT here is used for the attenuation corrections in that system.
Okay. Yeah, I think there will be more questions, but in interest of time, we'd like to now conclude. And I again thank Professor Moskal for an excellent talk.
Thank you very much.
Yeah. So please join us for tea and snacks in the cafeteria. And
thank you very much.